we were talking about all kinds of things, square roots. We discussed what exactly a square root was, what it does for us. Let me check something real quick. Yeah, that's fine. Anyways, so we were dealing with all things square roots. Last time we looked at taking a square root, like square root of 75, and branching off some things that would help us to simplify the square root. We said 75 was 25 times 3. We split the square roots up into two products. Square root of 25 ended up just being 5. 17, the square root of 17, well, 17's got nothing special about it. 17 is just not special. Every one of you in here and every one of you in the Zoom room is special. You mean something. 17 doesn't have any special things to do with the square root. So it doesn't have anything to simplify. It just is what it is, basically. So now what we can talk about is we can talk about, well, earlier we went one way. We said, okay, we have something inside a square root. We might want to split it up into separate square roots that we multiply together. We also might want to start off with two separate square roots, bring them into the same square root house, and see if anything good comes out of it. So you might say, well, the square root of 2 times the square root of 5, you're multiplying two separate square roots. You can bring them into the same house by saying it's just the square root of 2 times 5. Now, in that particular example, you might not want to do something like that. It may not do you any good. You just end up with square root of 10. That's great. I guess it simplified things. You got it all into one square root. But in this particular case, it didn't do anything truly wonderful for us. But this one here, square root of 7 times the square root of 7, something wonderful happens. Something magical happens, huh? We can put those 7s into the same square root house. 7 times 7 is 49, so they kind of skipped a step. But see, that would end up being square root of 7 times 7, because we put them into the same house. 7 times 7 is 49. Maron. We got square root of 49, which is just 7, no square roots. The square root's gone, baby, gone. So that's good. So sometimes there's cute little tricks like that that can help us simplify the overall production, everything that we're seeing. So that's what they did here. Finally, so let's say we're doing the square root of 6 times the square root of 12. The idea here is standing alone, square root of 6 by itself isn't really something that's going to be simplified in any kind of magical way. Square root of 12, there's some simplification you can do in that. But by bringing them together, there's a whole mess of extra things we can do. We take square root of 6 times square root of 12, put them in the same square root house. You get 6 times 12 inside of a single square root, and you got square root of 72. Now, 72 is a fairly large number, so it might be worth investigating whether or not it could be simplified in some way. And in fact, it can. 72 is just 36 times 2. Why do I care about that? Why didn't I say, well, it's also 18 times 4? Well, it's because 36 is the largest factor of 72 that is itself a perfect square. So that when I branch it off and I branch them into separate square roots, I get to take the square root of 36, which is just 6. And all I've got left over is the square root of 2. That's something else right there. That's very powerful stuff. If I would have made it 18 times 4 here, which I could do, well, I could bring that 4 out because 4 is a perfect square. But the square root of 18 inside there may still have some factors that could end up coming out cleanly. So what we did was we picked the largest factor of 72 that was a perfect square in and of itself. How about that? Any questions on that? Can you see why, kind of some of these little tricks are helpful? They're helpful. They make life a little bit easier. Now, the real question is, why are we learning any of this? Why do we care about any of this? And I'm no fool. I'm no fool. I get it. I get it. I'm not so lost in math that I can't see the forest for the trees. And the forest is, look, deep down, you probably don't care about any of this stuff. Okay, I admit that that's a possibility. But here's the thing, when we're going to get to the 1332 portion of this course, the second half portion of this course, we're going to be talking about some good stuff. We're going to be talking about finance, specifically your money. Now, how many of you would like to have as much money as you possibly can within your means? Yeah, I think you would. How many of you would like to buy a house or own a house or something like that? You'd like to buy a house. Why? Because buying a house takes care of, you got to live somewhere. When you buy, you get to do more things to your own house than you might in renting. You can modify it how you like. But a big thing is that, unlike cars, houses generally gain value over time, meaning that they're a good investment. So not only are you living somewhere, you're actually building good lifelong wealth through it. Buying a car, you're buying a car because you need a car. You might choose to own it so that you can at least pay it off and not have any more payments on it. But that car loses value the second you drive it off the lot. And it only generally loses value every year unless it's some kind of weird collector's car. But then you probably just keep it in the garage. Personally, I want to buy a DeLorean. How many of you know what a DeLorean is? From Back to the Future? I want to buy a 1980s DeLorean. I look at them all the time on the internet. And if I bought a DeLorean, it's a car that has the doors that open up like this instead of opening a door out. They're gull wing doors. They're really cool. I would never drive that thing. I would just keep it in my garage and I would come out, bless you. I would just come out and I would ogle it and I would look at it and I would sit in it and I would just say, oh, I'm just the happiest guy alive right now. I'd read stories to it. I would go out and read stories to an inanimate object because I love it. So anyways, buying a car is not a good investment for you in the long run, in most cases. Well, if you want to buy a home, you really should get the lowest monthly payment, right? And there's all kinds of factors that affect that. How long of a loan you want to pay off? 30 years is the standard. What's your interest rate? Is your credit good enough to get you a low interest rate? Things like that. So when we think in financial matters, we save money in the long run, and that's brilliant. That's exactly what we want to do. That kind of way, education is your way of equipping yourself to a better life. And I mean that. I'm not just BSing you because I happen to be in education and I have to tell everybody how great it is. I really believe that. You guys are all sitting in here. You're probably sitting in here to better your life, right? You're sitting in here to get an education, get better job, get higher paying jobs. That's why you're here. So that's the kind of math we want to equip ourselves with, and we need this kind of math to really talk about that on any kind of useful level. So it seems worthless at the moment, maybe. I don't believe that's actually true, but we're going to see how it's helpful shortly. And listen, that's not the only time you're going to hear me rant about that. This is just the first time. Maybe it's even the second time. I don't know. Yeah, it's probably the second time. You're nodding your head. Yeah, it's probably the second time. I'm going to rant about it a couple times because I really believe it. Okay, so back to it. And, you know, I'm trying to make it as entertaining as I can. We still have to talk about it. I can't just sit up here and do stand-up comedy. Would I be good at stand-up comedy? No. Why'd you remind me of that? Why'd you remind me that I'm horribly unfunny? I can't tell if anyone's smiling. Everyone's wearing these weird face devices and it covers your mouth. So I don't know if anyone's smiling or enjoying this. I'm just going to assume you're not. Okay. Anywho, continuing on. So we can simplify square roots and whatnot through multiplication. There's some kind of ways that we can do that. Well, it turns out we can also do quotients, meaning we can divide. Look at this. We have two separate square roots here. We have a square root on top divided by some kind of square root on bottom. Those are two separate square roots. Guess what? You can put them into the same square root house and just do the division all inside the square root. Huh? Ain't that something? Give that a round of applause. Go ahead. Everybody, yeah, you can put them in the same house. I want everybody in the Zoomosphere to give a round of applause at home. Go ahead. There's going to be honor system that you're doing it. Yes, you can put them into the same house if that's what your heart truly wants. You can also take a a fraction that, oh, here we go. You can also take a fraction that's inside a square root, division that's inside a single house, and you can split it up into two houses. Now again, why do we care about that? Well, it just might so happen that it helps us in some way of simplifying things. It helps take something that looks nasty and complicated, and it kind of makes it a little less nasty, a little less complicated, a little bit easier to digest. So for instance, you have square root of 75 and separately the square root of 3. Well, in this particular case, it might make sense for us to put them into the same square root house. Let's just work that together. So you're starting with square root of 75 divided by the square root of 3. Now, square root of 75 is not going to be pretty. It's not a perfect square. It's in between 64 and 81, so it won't be a perfect square. Square root of 3 won't be pretty. So you might think that the square root of 75, which is a nasty number, divided by the square root of 3, which is a nasty number, is going to produce a nasty number. How many of you would just naturally think that? Yeah, nasty divided by nasty. Well, guess what? This is a case where the nastiness divides itself out, if you will, and there's going to be no more nasty with this. Because we have two separate square roots, let's put them in the same house. Let's put them, and that's using that rule we just gave ourselves, we just equipped ourselves with. And now, well, we have a single fraction inside the square root, so let's divide 3 into 75, which is what? Yeah, it'll end up being 25. With no remainder. It'll be 25 perfectly on the dot. So square root of 75 over 3 becomes just the square root of 25. Hey, give it another round of applause, huh? Let's do it. Round of applause. Mr. Gunther, it's 9:20 in the morning. I'm drinking an energy drink, which I'm joining you now. You're drinking coffee. I just don't feel like applauding in the morning. Well, guess what? I'm still going to ask it of you. You don't have to do it. You guys are all adults. I'm not teaching high school, middle school, elementary school for a reason. I don't want to teach. I don't want to have to be a disciplinarian. That's not who I am. I'm not a disciplinarian. You guys are all adults. I love teaching adults because you guys just naturally are polite and you're here to learn. You're paying money to be here, so you're not going to screw around, right? That's the idea. That's why I love teaching adults. So anyways, we simplified that into square root of 25. What's the square root of 25? 5. Hey. Handel's Messiah is playing in the background because it becomes nice and easy. So square root of 75 divided by square root of 3, while it looks nasty, it ain't nasty. It ends up just being a nice 5, and there's nothing more to it. Any questions on that one? And remember, in the Zoomosphere, you can always use the chat box. Always use the chat box. So we ended up getting the same result. Now let's look at part B here. We got square root of 90 divided by square root of 2. Again, they're in separate square roots. We'd like to put them into the same house because maybe there's some simplification that can be done when we do that. And that's exactly going to be the case. You put them into the same house, you get square root of 90 divided by 2. Now, 90 divided by 2, you might be able to eyeball it that it's 45, or you're always free to do long division. You're going to get no remainder, and you're going to get 45. So we just end up with the square root of 45. And that's kind of why we did that. We brought them into the same house. Oh, even better, we can write 45 as 9 times 5. Why did we do that? How come we didn't write 45 as 15 times 3? Right. 9, basically, we branched out the largest perfect square factor of 45. If we would have written it as 15 times 3, which is still what 45 is, well, 15 is not a perfect square. 3 is not a perfect square. That doesn't help me. But if I write it as 9 times 5, 9 is a perfect square. It's the largest perfect square factor we can get. And so by doing that, now we branch them off into 2 separate square roots. Square root of 9 is 3, and so we end up with 3 square roots of 5. The square root of 5, nothing can be done about that. That's as simple as it gets. So the point of a lot of these rules, we're going to learn that these are actually just general exponential rules. And what's really going to blow your mind, you're going to find out, just like we were taking exponents, like squaring something is multiplying it to itself. Raising it to the third power is multiplying it to itself 3 total times. We're going to learn that the square root is taking a 1/2 power, which sounds weird, but that is the definition of it. So these are actually all just exponential rules you're learning. Now, before we jump into this, raise your hand if you've ever heard the phrase like terms in math. Like terms, like terms, like terms. They like each other. So in math, and this is kind of, we're looking ahead to the future. In math, 2 things are like terms if they have the same variable setup. So if you have 5x and then you over here you have negative 12x, well, both of them just have the variable x. So they're like terms. X squared is not a like term with something that's just x, because you have to have the same variables and they have to be raised to the same powers. So like terms, whenever you have them, what do you often like to do with them? If you have 3x plus 5x, what would you do with that? Add them together. You would combine like terms, exactly. So just like terms, if you had 3x plus 5x, they have the exact same variable setup. This is just x to the first. This is just x to the first. Excuse me. Now they have different coefficients. This one has a 3 in front. This one has a 5 in front. That's okay. The coefficients can be different. The variable setup has to be the same. And so what you're telling yourself is it's like, I got 3 apple pies. I'm adding 5 apple pies to that. So how many apple pies do I have in total? 8. So it's going to be 8x when you combine like terms. Exactly. Yeah. X squared is technically doing something different. But yeah, that's a good thing. He was asking, well, would it end up having the x squared on it? No, it wouldn't. If you were to multiply them together, if I was doing 3x times 5x, it would end up being x squared. Well, when I just add them, there's no squaring that comes about. Good question. You can also see funky like terms like this. 2 x squared y z to the third. Well, that looks nasty. You just have an x squared, a y, and a z cubed. If I was doing this, these are still like terms. Don't get horribly caught up. You see you have an x squared here, times a y here, times a y here, times a z to the third here, times a z to the third here. So don't let yourself get caught up. These are still like terms here because they have the exact same variable setup. They have the same variables themselves, and all the variables have the same powers on them, exactly the same. So these are still like terms. So you just have 2 of something minus 8 of that same thing. Now you can't really subtract 8 apple pies from only 2 apple pies in real life. But if you understand the idea of negative numbers, we can allow this to go negative. And that'll end up being -6 of whatever that object is. And that object just happens to be x squared y z to the third. So you still have like terms in that case. And you're going to see how this applies here. This is also good because we're going to be getting into like terms again in just a matter of weeks. Yes. Because what we're doing, let's say just for kicks, in order to make a real world analogy to this. Let's say that was 12 of that business minus 8 of that business. So if you have 12 cans of Red Bull, 16 fluid ounces, gives you energy in the morning. If you have 12 of these Red Bulls and someone takes 8 away from them, you have how many Red Bulls now? 4. But did I alter the structure of the Red Bull or anything? No. So that's kind of an analogy for this. This is just the object itself that we're kind of bartering around. Now, if we were to multiply things together or divide things, then you could talk about cancellation, but we're just doing subtraction. So then in this case, it would end up being positive 4 x squared y z to the third. Now let's play with it. Let's mess with it. That's always good. What if I did this, but everything else stayed the same? I knocked a 3, the cubed, off that z in the second one. Are these like terms anymore? No, these are no longer like terms. Now I can still say it's this thing minus this thing, whatever the heck it's supposed to represent, but there's nothing cool or slick that I can do to try and simplify that. I can't squeeze them together. So this is now as simple as it gets. That would be like if I had 12 cans of 16 fluid ounces original Red Bull, and I was trying to subtract off 8 cans of that nasty, like acai berry Red Bull that they have. They're not the same flavor, so it's not apples to apples anymore, if you will. Now, an apples flavored Red Bull, actually, that'd probably be pretty gross. But anyways, actually they do. No, they have pear. That's what it is. Anyways, so they're only like terms if they have the exact same variable set up. So now let's draw an analogy to square roots. If I have 5 square roots of 3 and I add 17 square roots of 3. You can almost think of these as like terms. With the common object being, earlier it would have been some kind of weird variable thing like x squared y or x. Here the common object is going to be the square root of 3. That's what it's going to be. And so now this is just like saying I have 5 of this object and I'm adding 17 of this object. So I add the 5 and the 17. What's that going to give you? 5 plus 17, 22. And so now I just have 22 of that object. I have 22 square roots of 3. What about this thing? 7 square roots of 11 minus 9 square roots of 11. Perfect, exactly. Now it's going to go negative because 7 of something minus 9 of something. Well, you can't do that in real life. You kind of can. You can think of it still and extend it to the negative numbers. 7 minus 9 is negative 2, and the object of my, the whole point of this is that I'm talking about the square root of 11. So when I have 7 square roots of 11 minus 9 square roots of 11, I end up with negative 2 square roots of 11. So the same mathematical rules apply. You can just think of the square root of 3 now like it's its own special object, just like we did with variables before. And you can think of it as just you're combining like terms. All right, let's mess it up a little bit. What if I just had that?
That'd be a 9, negative 9.
You're close. You're very close. You have the square root of 11 minus 9 square roots of 11. This first guy, how many square roots of 11 do you have there? You have an implied 1, yeah. If there's nothing written in front of it, it's implied to be a 1. You couldn't say there's 0 of them because there would be nothing there. So if there's not a coefficient written, it's automatically implied to be a coefficient of 1. So now you have 1 of it minus 9 of it. What will that give you? Negative 8, yeah. You'll end up with negative 8 square roots of 11. So don't let that throw you off. Let's play with it some more. Let's play with it some more. Let's say you have 5 square roots of 11 minus 9 square roots of 13. Are these still like terms? They're not anymore. You can't think of them because the linking object that was making them like was what was in the square root, basically, was the square root of 11. But now this is the square root of 13. So these are no longer like. They're no longer like terms. So 5 square roots of 11 minus 9 square roots of 13. This can't be simplified any further. It's just some weird number. We can do that in the calculator. We could do 5 times the square root of 11 minus 9 times the square root of 13, but it's just going to give you some ugly number. And there's no simplifying to it. Any questions on that thus far? Is it clicking? Again, you're always free to ask questions. I'm always happy to answer questions. And if you want to ask me questions about my future DeLorean purchase, those are always appreciated, because I will be purchasing a DeLorean someday. 30K, which is certainly, it's not like I'm buying a Lamborghini or a Lotus or something, like a $200,000 car. Yeah, for 30, you can get like a DeLorean. I found a dealership in Florida. You can get a DeLorean that has less than 50,000 miles on it. And it's in primo. I mean, it's not like I'd ever drive it anyways. I would just cradle it at night. But anyways, so yeah, 30K is still a lot of money, but that's why it's like my dream purchase, right? That's like my one day I'll have it, if I save my money now and I'm smart with it, one day I'll be my own Marty McFly, I could do that, yes. I've never been very good at boating though. That's been another one of my secret passions, is to go boating. I actually routed out, you go from Galveston and you go the entire Gulf Coast and all the way up the East Coast to Maine into Canada, and then take that trip back. And I could do it in 90 days if I was steering the boat like 8 hours a day, and it would cost thousands and thousands of dollars. But I've thought about it. I've thought about doing that. That'd be cool. But yeah, so DeLorean has to come first though. Okay, I have my priorities, guys. Anyways, so this is just what we just did here. This is exactly what we just did. 7 square roots of 2 plus 5 square roots of 2. The linking object is the square root of 2. That's like your x. And x is going to give it to you here. In this case, we're going to add the 7 and the 5 together. And we're going to end up with 12 square roots of 2. 7 plus 5 is 12. Over here, we have 2 of some object minus 6 of that same object. It's going to go negative 4 of that object. Negative 4 square roots of 5 in this case. So it's really good to think about it as like terms. Another reason, and you asked a really good question, how come like the x's didn't cancel out? It actually has to do with order of operations. It actually has to do with order of operations. The reason is that exponents, multiplying and dividing, all come before addition and subtraction when you're doing order of operations. But since you don't know what x, y, or z are, they're variables with unknown values, you can't do any of the squaring, multiplication, or division yet. So the only thing you can do is addition or subtraction. So you got to do the addition or subtraction and then wait till you have values for X, Y, and Z before you can try anything fancy with that. So that's just another reason, another way to think about it. And then this last thing, I don't agree with having to learn it. So how many of you were alive during the 70s? Anybody? Anybody? Maybe you were, maybe you weren't. But in the 70s, you had computers, which were not as powerful as computers we have today. Although interestingly, in the 70s, IBM made a was it IBM? I think it was IBM or Dell made a microchip the size of your fingernail that was more powerful than computers 30 years earlier that used to be the size of this room. So even in the 70s, they still had some pretty wicked stuff. But anyways, old school computers did not like dividing by irrational numbers. An old school computer, an old school calculator, you have the square root of 6 here. A computer didn't like to divide by that. It wanted to divide by like a nice solid 6 and just be happy. The reason is, if you think about long division, the number you're dividing by, you want that to be the simplest number. So you don't have to try to get wild and crazy with it and have like a 12-digit number you're dividing by, and then you have to think, how many times does this 12-digit number go into my, it gets nasty. So old school computers didn't like dividing by square rooted numbers like that, irrational numbers. So what you would have to do is, before you could put it into the computer, you had to rationalize the denominator, meaning you do some cute little trick that gives you the same number in spirit, that's true value is the same, but suddenly you're not dividing by an irrational number anymore. And then the computer would say, thank you, and you'd be fine. So rationalizing the denominator is, I guess, fairly interesting, but it's no longer relevant because my little silly calculator app on my phone, everybody's little calculator app on their phone can perform calculations literally thousands of times faster than the computers we sent man on the moon with. We literally put man on the moon with computers that were comparatively a lot slower than what you have in your pocket today. It's kind of wild if you think about it, but that's just how it is. So we'll just survey this real quick. We'll look at it. 15 divided by square root of 6. Well, the square root of 6 is irrational. I don't want to divide by an irrational number. Remember, an irrational number is one that the decimal goes on forever without repeating. Okay, so what can I do? I can use some silly little trick here. I can multiply this by the square root of 6 divided by the square root of 6. Why? Because this business here, this is just equivalent to 1. Something divided by itself. Square root of 6 divided by itself. 3 divided by 3 is 1. Negative 25 trillion divided by negative 25 trillion is just 1. So I'm really multiplying by something divided by itself. I'm just multiplying the number by 1, but it's a tricky, cute little way of multiplying by 1. Because now I'm going to have 15 square roots of 6 on top, but on bottom, this square root of 6 times square root of 6 becomes square root of 36, which is just 6 by itself. And suddenly I have freed my denominator of any irrational numbers. And then 15 divided by 6 can be reduced to like 5 over 2, as if it were a fraction. So similar business going on over here. You had square root of 3 over square root of 5. Okay, well, rewrite it as multiply it by this thing times itself, and you end up with no irrational number on bottom. And that's the whole point of it. Again, it was to appease computers in the 70s, so I don't know why textbooks today still really teach it, because it's just a cool little trick and everybody had to learn it. So they're like, we should make the next generation learn it. So there you go. Computers, wow. Okay. Let me queue up the next thing, the next guy or gal, whatever your fancy. Whatever you like. So we're going to talk about real numbers. We've actually already talked about real numbers. In fact, last time we defined real numbers and we said, well, real numbers are numbers that are either rational, and rational numbers can be fractions, they can be integers, they can be natural numbers, or a real number can be irrational, which is to say, if I express it as a decimal, it goes on forever without repeating. And then those are the only two types of numbers. Now, this little chart they have here, they included something called the whole numbers. We're not going to worry about that. We just have natural numbers, integers, rationals, irrationals, all together. A number that is either a rational or is irrational, and it has to be one or the other, it can't be both. That is called a real number. That's what a real number is. That is what a real number is. And we already looked at this chart last time. We defined it. We said the real numbers have this special symbol. It's like an R, but with some extra cheddar on it. Now, how many of you see the word real number and you immediately think, well, what is an unreal number? Or what is real about it? Does anyone, maybe you're thinking that? Why is it called the real numbers? Because we have real numbers, but recall, so we have real numbers. How many of you have ever heard of imaginary numbers? Imaginary numbers, maybe just. Now, really, the word imaginary is kind of a bad word for it, because if you think about it, all numbers are imaginary in the sense that it's just some kind of system we have imposed on the natural order of things. The fact that I have one Red Bull in my hand is just a definition that we as human beings have made. The number one itself doesn't actually exist, like the actual can of Red Bull is made of aluminum and whatever they use to paint the can. So technically, an imaginary number is no more real or imaginary, but because it's not a number that you're going to see happen a lot in real world applications, we kind of don't do it. So imaginary numbers, really, they're called complex numbers, and they involve a little digit called I. And you may have seen that if you took algebra. I is defined as the square root of a -1, which itself seems like there's something wrong with that. So we will not ever touch the imaginary, or AKA the complex numbers again in this course, or maybe very briefly if we do. But it's just so you know, there's imaginary numbers in math. What the heck are they? Let's not have that conversation because it's irrelevant. Let's not waste our time on it. But there is very good applications and reasons, especially in engineering, for imaginary numbers. Okay, so we have real numbers. Those are what we're going to focus on. A real number is either rational or irrational, must be. So let's take each of these numbers here. Let's start with -7. Let's put the spotlight on it. -7, come on down. So we're looking at -7. We're not going to worry about the idea of being a whole number. Who cares? A whole number is literally just the positive integers plus 0. That's so uninteresting to me, or at least that's how they define a whole number. Okay, so what we're going to do is we're going to take -7 here, and we are going to circle all the labels we could apply to it. And there could be multiple labels here. So is -7 a natural number? Are you sure? What was the definition of the natural numbers? Those are positive whole numbers. So natural numbers got to be positive whole numbers. So -7, nope, not natural. Is it an integer? Well, remember the definition of an integer was either a positive whole number, 0, or the negative versions of all the whole numbers. Thus, -7, yeah, you are an integer. Good work. Is it rational? Remember, a rational number could, if you wanted to, could be expressed as a fraction of integers, one integer on top, one on bottom. Is it a rational number? Yes, because I could just call that -7/1 and be done with it. And remember, all integers are automatically rational. The second you identify something as an integer, it is forced to be rational. Now, it can't be irrational if it's rational. Irrational means not rational. That's literally what the word means. So it can't be that. Is it a real number? Yes, because all real numbers are either rational or irrational. Thus, if you've already identified it as a rational number, it's automatically real. So for -7, these are all the labels that could apply. It's an integer, it's rational, and it is also real, just by definition. Okay, let's zoom in on -3/4. -3/4. We're not going to worry again about whole numbers. Is -3/4 a natural number? Definitely not. First of all, it's got to be positive. And even if it was positive, it's not a whole number. 3/4 is in between 0 and 1. So it's definitely not natural. Is it an integer? Still no, because the integers are either the positive whole numbers, or it could be 0, or the negative versions of all the positive whole numbers, -1, -2, -3, -4. -3/4, again, is somewhere in between two otherwise whole-ish numbers. So again, it is not an integer, still not. Is it rational? Yes, because a rational number is just a ratio, it's a fraction of two integers, or could be expressed as such. 3 and 4 are both integers, even though you slap a negative sign in front of it, that's okay. It's rational. Is it irrational? Can anything be both rational and irrational? No. Can anything be both x and the opposite of x at the exact same time? Probably not, except in a postmodern world, maybe. So no, it's not irrational. Is it real? Yes. All rational numbers are automatically real numbers. So for -3/4, the two labels that can apply are it's rational and it's real. Let's pick a different color. We're not going to worry about whole numbers. Now let's look at SETO. Big fat stinking 0. Is 0 natural? What are the natural numbers? They are the positive whole numbers. So is 0 positive? Not quite. 0 is the only number that is neither positive nor negative. It sits in between them, but it's neither one of them. If you go just to the right of 0, you're in positive territory. You go just to the left, you're in negative territory. But 0 itself is neither positive nor negative. So we can't call it a natural number. But we can call it an integer. An integer is either positive whole numbers, 0, which we have here, or the negative versions of the whole numbers, -1, -2, -3. If it's an integer, it's automatically rational. All integers automatically are rational. If it's rational, it's automatically not irrational. And if it's any of these, it's going to automatically be real. The only way you get away from the real numbers for our purposes is if that little I character was involved, and it's not. So 0 is an integer, it's rational, and it's real. All those labels apply. All right, here's a potentially tricky one. 0.6, but it has the little bar over the 6, meaning the 6 repeats forever and ever. So really, that's the number, 0.66666666666, and then the 6's go on forever. Is it natural? Is it a whole number? Clearly not. And even though it's positive, it's definitely not natural. We're not worried about whether it's a whole number. Is it an integer? Is it an integer? No, it's clearly not an integer, because integers got to be 0, or they can be positive whole numbers like 1, 2, 3, 4, 5. 0.666 is in between 0 and 1, so it can't be an integer. Is it rational? Yes. A rational number, remember, is a number that, as a decimal, it either terminates, it stops, it's done, or if it does go on forever, it repeats. It repeats a pattern, which this one clearly does. So this one is rational, which means it's automatically not irrational. And then anything which is a rational number is just clearly automatically real. So we're getting a little bit warmer. We're getting a little bit warmer. So remember, the natural numbers are positive whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to infinity. You can't have anything in between the two whole numbers. 0.5 is not natural because it's in between 0, it's in between 0 and 1. It's got to be positive, and it's got to be just a nice regular whole number. Another way to think about the natural numbers, you can call them the counting numbers. You don't count 0.73, 0.1274. You don't count like that. You count 1, 2, 3, 4, 5, 6. You don't count parts or anything like that when you're doing simple counting. All right, let's just keep on going. We're having fun here. It's Kelly and Wine Mixer, and we've got 0.5. We're not worried about whole numbers yet again. And but not 0.5, square root of 5, excuse me, square root of 5. Now remember our conversation yesterday. When you take a square root, your first thought should be, there's a pretty good chance it's going to end up being irrational. Because taking square roots will usually produce a number, a decimal that goes on forever without repeating. It just keeps going and going like the Energizer Bunny, and it doesn't repeat. So the only exception is if I try to take the square root of something that is a perfect square already. So if I take the square root of 1, it's just 1. If I take the square root of 2, that's nothing special. But if I take the square root of 4, what is that going to give you? What is the square root of 4? 2. Because when you're taking the square root, you're asking, what's a number that multiplies to itself to give you 4 in that case? So is 5 a perfect square? No, it's not. It's in between 4 and 9, which are perfect squares. 5 is not a perfect square. So automatically, it's going to, if I tried to put it in a calculator, and you can try it if you want in your phone calculator, do 5 and then hit the square root button, you'll see it's going to give you a nasty decimal that's not going to repeat. So 5 certainly couldn't be natural. It couldn't be an integer. And because it's a square root of something that's not a perfect square, it's pretty much just by definition irrational right off the bat. I can go straight to that. But even though it's irrational, it's still real. All of these are going to be real, unless you try to bring I or any imaginary nonsense into the mix. So, square root of 5 is both irrational and real. Look at us, we're having fun, huh? How many of you are having fun? Raise your hand. I'll close my eyes. Raise your hand if you're having fun. None of you are having fun. Why not? Maybe I need to talk more about my future DeLorean purchase. Maybe that'll make things fun. Okay, pi. You'll recall yesterday, pi was one of the classic examples we gave of an irrational number. Pi is 3.14159. That thing keeps going and going and going and going. It doesn't ever repeat any pattern. So if it's automatically irrational, that's one you're just going to need to know. Pi is one of the famous examples of an irrational number. So it can't be rational, and then that automatically rules it out from being an integer or a natural number. No questions asked. But because it's not imaginary, it's still real. So having some fun. Come out to the coast, we'll get together, have a few laughs. How many of you know what that's from? No, but you're close. The Catalina Wine Mixer was. That's from Die Hard, which is a classic American action film, wonderful movie. And that's when he's like crawling around in the vents and he's trying to fight terrorists, played by Alan Rickman, aka Severus Snape from the Harry Potter movies. In case you can't tell, I don't like movies. I hate movies. Gross. Get movies away from me. All right, 7.3. We're almost done with this little portion. Maybe you're hoping for it. 7.3. That's a decimal number. Does it go on forever? Is there a bar on top of it? No. It's just 7.3 and it stops. It terminates. Now, it can't be natural because it's not a whole number. It's not a positive whole number. It can't be an integer because an integer is still got to be positive, negative, or zero, but it's got to be like a whole number. No decimals allowed, no weirdo decimals. So it's not an integer. Is it rational? Remember, the two definitions of rational are either it's a decimal that terminates, which this does, or it's a decimal number that goes on forever but repeats. So it is rational, automatically could not be irrational, and then it's also real. It is also real. Finally, let's do Lello. Square root of 81, that's too light. You can't really see it very well. We'll do brown. Square root of 81. That one's trying to trick you. Don't let it trick you. You see a square root, so your mind shouldn't think it's automatically irrational, but your mind should be wondering, could that be irrational? It's a good candidate for one. Exactly. Square root of 81 is just 9. It's just another way of representing the number 9, because 9 times 9 is 81. So if I take the square root of 81, I go back to 9. So don't let this one throw you off. This is a great trick question, because the square root of 81 is just the number 9. So square root doesn't automatically mean irrational. It just means you should be thinking irrational and then make sure it is or isn't. So we're really just looking at the number 9. Is 9 a natural number? Bet your bottom dollar there, Pilgrim. It's a positive whole number. So 9 is natural. We're not worried about this. Is it an integer? Absolutely. A natural number is automatically an integer. An integer is automatically rational. A rational is automatically not irrational. A rational is automatically real. So hopefully, I know that was a little bit long and painful, but hopefully that gives you a nice painstaking understanding of the different types of numbers that we're going to concern ourselves with. You really want to know those differences. Okay, let's not go anywhere. Please stay in Zoom as well. I'm going to take attendance.